If you've been following this channel, you know that all of our recent deep dives have focused on the comet and its baffling anomalies. But I cannot remain silent about what is unfolding now. 2025 into 2026 has become a year of unexplained celestial phenomena. First, we had the comet behaving in ways that challenged our models. Now, the Sun itself is exhibiting behavior that has the astrophysics community on high alert. There is a pattern emerging here, a convergence of anomalies that demands our attention. And what is happening on our star right now may be the most significant development yet. In early February 2026, the Sun suddenly entered an unusual state that has already drawn heightened attention from astrophysicists around the world. We are looking at a giant active region with an extremely complex magnetic structure that has formed on the solar surface. Within just a few days, this region began producing a series of powerful flares, acting as if an unstable energy mechanism had been triggered inside the star. This is not just standard solar weather. In a short period of time, some of the most intense events of the current solar cycle were recorded, but their development proved to be atypical. The data we are analyzing shows that energy is not only being released into space, but is also partially retained within the region itself. This is creating the specific impression of accumulation before a possible next stage. If you want to stay ahead of these rapidly developing solar events, make sure you subscribe to the channel right now so you do not miss the updates coming in later this week. To understand why this is catching everyone off guard, we have to look at how these systems usually behave. Normally, active regions on the Sun follow a predictable pattern. They either discharge rapidly through a series of eruptions, blowing that energy out, or they gradually weaken over time. In this specific case, however, we are observing an unusual combination of growth, density, and stability. The region is continuing to intensify despite having already produced major flares. It is behaving unlike anything we would expect from a standard decay model. This creates the impression of an unstable equilibrium, a state in which the system balances precariously between gradual decay and a sudden, more powerful release. In the past, similar phases have sometimes preceded the largest solar events in recorded history, making the current situation especially intriguing for everyone watching the monitors. The sheer scale of this magnetic complexity suggests that the internal dynamo of the star is working through a unique hitch. We are seeing raw power output that rivals peak cycle statistics, yet the structural integrity of the active region remains strangely intact. It is refusing to break down. When we look at the magnetograms, the field lines are twisted and dense, locking that plasma in place even as the flares detonate. It is a retention event. The energy is building up, layer upon layer, rather than dissipating into the void. This accumulation effect is the critical anomaly. Typically, a flare acts as a valve release. The magnetic lines snap, reconnect, energy blasts out, and the local system relaxes. We are not seeing that relaxation here. We are seeing the tension remain high. We are seeing the complexity increase rather than decrease after each event. It is as if the Sun is winding a spring tighter and tighter, even as it lets off sparks. This suggests that the mechanism driving this active region is far more fed by the deep convection zone than a typical sunspot group. the energy finding its way to the surface is hitting a bottleneck, a magnetic cage that is trapping it. And this is where the mystery deepens. The data coming in from the last 48 hours shows that despite the high intensity of the flares, the actual mass leaving the Sun is confusingly low. We are not seeing the massive coronal mass ejections we usually associate with flares of this magnitude. The proton flux is not spiking in the way simple models would predict. The energy is there. The flash is there. The ultraviolet and X-ray radiation is screaming off the surface. But the physical matter, the heavy plasma, it is staying put. It is being held back. This contradicts simplified models in which a strong flare is almost always accompanied by a powerful mass ejection. Here, it appears as if energy is trapped within the magnetic structure and has not yet found a full outlet. We are watching a sealed system under immense pressure. The implications of this are significant because it means the total energy budget of the region is not being depleted. It is being conserved. And in physics, conserved energy in an unstable system inevitably looks for a way out. This brings us to the concept of the unstable equilibrium. Imagine a ball sitting at the very peak of a sharp mountain. A small push could send it rolling down one side toward a quiet, gradual return to normal. But a push in the other direction could send it plummeting down a sheer cliff of extreme activity. That is where this active region sits right now. It is teetering on that edge. We are observing minute-by-minute variations in the magnetic shear that tell us the forces are fighting for dominance. The forces of containment versus the forces of eruption. The fact that we are seeing this accumulation phase specifically in February 2026 is also noteworthy. It places this event firmly in the context of the current solar cycle's maturity. We are not in the quiet accumulation phase of a solar minimum. We are in a dynamic period where the Sun is already active, yet this specific region is behaving like a singularity. It is hoarding power. It is acting like a battery that refuses to stop charging, even as it arcs electricity into the surroundings. Researchers are currently debating whether this accumulation is a prelude to a saturation point. If the region continues to trap energy, the eventual release could be exponentially larger than the individual flares we have seen so far. Or it could manage to dissipate this energy thermally, glowing hotter and brighter without ever producing a catastrophic ejection. That is the needle found in the haystack of data we are parsing through. The ore, the uncertainty. We are watching the inputs. We are watching the magnetic flux rise. We are seeing the geometry of the sunspots twist into configurations that are historically associated with superstorms. Yet the storm has not fully broken. It is a suspended animation of violent potential. The flares are the warning shots, but they are not the main event. They are symptoms of the underlying pressure, not the cure. As we move forward into the analysis of the physics behind this, keep in mind that accumulation is the key word. Energy cannot be destroyed. If it is not leaving the Sun, it is staying there. And if it is staying there, it is changing the local environment in ways we are just beginning to model. The magnetic loops are getting heavier with plasma. The thermal pressure is rising. The system is pushing against its own restraints. In the next part of this deep dive, we are going to look specifically at the mechanism of this trapping and why some scientists are comparing this active region to a piece of industrial machinery gone wrong. We need to talk about the overheated boiler hypothesis and what happens when the safety valve fails to open completely. Because that is exactly what the spectral lines are telling us is happening right now. As we established in the previous discussion regarding the abnormal energy accumulation in this new active region, the core mystery lies in the missing mass ejections. We have the flares, we have the intense flashes of radiation, but we do not have the corresponding expulsion of solar material that usually acts as the release valve for these magnetic systems. This brings us directly to the physics of what is happening inside that magnetic cage. Some researchers are now comparing this situation to an overheated boiler in which pressure keeps rising while the valve remains partially closed. It is a vivid and perfect analogy for what the data is showing us. In a standard solar event, the magnetic pressure builds up until it overcomes the structural integrity of the field lines. The lines snap, the valve opens, and the plasma blast carries that excess energy away into the heliosphere. The boiler vents its steam, but here the valve is sticking. The energy is flaring. It is heating up the local atmosphere to incredible temperatures. But the magnetic structure is so robust, so dense, that it is trapping the bulk of the plasma inside. Additional mystery lies in the fact that some plasma ejections have been relatively weak despite the high intensity of the flares. This is the smoking gun of the trapped energy hypothesis. When we analyze the coronagraph images, we expect to see huge halos of gas expanding outward after an X-ray spike of this magnitude. Instead, we see puffs. We see minor streams. It creates the impression that the accumulation we discussed earlier is acting like a heavy lid. The pressure is rising, but the lid is holding it down. This contradicts simplified models regarding solar eruptions. We are taught that A leads to B. A strong flare leads to a powerful mass ejection. That is the baseline. But here, it appears as if energy is trapped within the magnetic structure and has not yet found a full outlet. This creates a state of internal stress that is difficult to simulate. The magnetic field lines are likely incredibly twisted, essentially tying themselves in knots that are too strong to be blown apart by the initial flares. Think of it like a knot in a rubber band. You can twist it and twist it, storing more and more kinetic energy. Normally, it snaps, but if the rubber band is thick enough, it just keeps twisting, storing that energy, vibrating with tension. That is the unstable equilibrium we are observing. The system is balancing between gradual decay, slowly untwisting, and a sudden, more powerful release, where the entire structure fails at once. Within the scientific community, the possibility is already being discussed that we are witnessing a rare type of active region evolution that is poorly described by existing models. We have to be honest about the limits of our knowledge here. Modern solar physics explains individual flares well. We understand magnetic reconnection. We understand how particle acceleration works on a local scale, but it struggles to predict complex cascade processes in which dozens of events follow one another without destroying the region's overall structure. Usually, A cascade of dozens of flares tears the active region apart. It exhausts the fuel. It simplifies the magnetic field. But here, the region continues to intensify despite having already produced major flares. The complexity is increasing, not decreasing. The boiler is getting hotter. The pressure is rising. And the valve is still only letting out a hiss of steam when it should be blowing the whistle. This suggests that the magnetic field configuration is surprisingly resilient. It is effectively self-repairing or self-reinforcing after each flare. Instead of the flare breaking the magnetic cage, the cage snaps back into a tighter configuration, perhaps even trapping more heat and plasma than before. This feedback loop is what is creating that impression of unstable equilibrium. We are looking at a scenario where the energy density within this active region is climbing off the charts. Because the energy is not escaping as kinetic motion of a coronal mass ejection, it has to go somewhere. It is being converted into thermal energy, heating the plasma to millions of degrees, and into magnetic potential energy, twisting those field lines tighter. This is the definition of a trap, and trapped energy in a stellar environment is a volatile variable. It implies that the system is searching for a new stable state, but the path to that stability is blocked by its own complexity. It is like a traffic jam where no one can move, but the engines are revving harder and harder. I want to hear what you think about this analogy. Does the overheated boiler make sense to you? Or do you have another way of visualizing this trapped energy? Leave a comment below with your thoughts on how a star can hold on to this much pressure without blowing apart. The struggle to predict this comes from the fact that we are dealing with magnetohydrodynamics on a scale that is impossible to replicate in a lab. We are watching a natural experiment where the variables are set to maximum and the controls are broken. The fact that the region has not yet destroyed itself is the anomaly. It creates a scenario where the eventual outcome is binary. Either the boiler cools down slowly, dissipating that heat through months of low-level sizzling, or the valve fails catastrophically. The accumulation implies the latter is a distinct possibility. We are seeing a system that is resisting the release, and in physics, resistance often leads to a more violent breakdown when the threshold is finally crossed. So, we have a giant magnetic structure, structurally sound, but internally screaming with tension. We have weak ejections from strong flares. We have a boiler that is ticking. This leads us to question the very phase of evolution this active region is in. Is it a freak occurrence, or is it a transition? In the next chapter, we are going to explore the idea that this is a specific transitional phase between two known regimes of solar activity. We will look at why some experts think the system is oscillating, effectively stuttering, as it tries to decide whether to stabilize or shift into a radical mode of extreme release. Building on the concept of the overheated boiler and the trapped energy we just analyzed, we must now pivot to the theoretical side of this event. Why is the sun behaving this way? Why is the valve stuck? From a speculative perspective, it cannot be ruled out that the active region is in a transitional phase between two regimes. We are used to thinking of solar activity as on or off, quiet or storming. But nature is rarely that binary. What we are seeing now suggests a gray area, a liminal space between moderate activity and extreme release. In such transitional states, a system may oscillate for a long time, producing a series of strong but incomplete discharges before either stabilizing or shifting into a more radical mode. This matches the data we are seeing perfectly. The series of strong but incomplete discharges is exactly how we would describe these intense flares with their weak mass ejections. The system is stuttering. It is trying to shift gears. It is oscillating. It flares, tries to release the pressure, fails to fully eject the mass, and then settles back into a high-tension state, only to try again. This implies that the magnetic dynamics are caught in a feedback loop. The forces attempting to tear the magnetic field apart are almost perfectly balanced by the forces holding it together. This balance is what creates the oscillation. It is not a stable piece. It is a wrestling match where neither side is winning. And because neither side is winning, the energy continues to build and the region continues to churn. In this sense, what is happening resembles a natural experiment that tests the limits of our understanding of stellar magnetic dynamics. We are watching a stress test. The universe has essentially set up a laboratory on the surface of the Sun, cranked up the parameters to critical, and is waiting to see what breaks first. This uncertainty is precisely what makes the situation so fascinating for observers. We are scientists, but we are also spectators in a cosmic arena. We are watching the process in real time without knowing which scenario it will ultimately follow. Will the moderate activity regime win out, leading to a slow, harmless dissipation of the active region? Or will the extreme release regime take over, triggering a sudden radical shift in the system's behavior? The term radical mode is not used lightly here. If the system shifts, it could mean a complete restructuring of the local magnetic environment in a matter of minutes. This is the sudden, more powerful release we touched on earlier. If the transitional phase ends with a breakdown of constraints, the accumulated energy we discussed in Chapter 1, that trapped energy, becomes the fuel for an event that goes far beyond a typical solar flare. Modern solar physics struggles to predict these transition points because they rely on nonlinear triggers. A tiny change in the magnetic shear, a small injection of plasma from below, could be the grain of sand that causes the avalanche. Or it could be the grain that settles the pile. We do not know. This is why we say the active region is poorly described by existing models. Our models are great at predicting the arc of a ball once it is thrown. They are terrible at predicting exactly when the pitcher will decide to throw it. We are in the winding up phase, and the pitcher is hesitating. The idea of this being a natural experiment is key. Every time the Sun does something unexpected, we learn more about the fundamental laws of plasma physics than we do in decades of theoretical simulation. We are learning about how magnetic flux ropes can endure stress. We are learning about how energy can be sequestered in the solar corona. We are seeing the limits of our understanding being mapped out in real time. It is important to emphasize that this oscillating behavior effectively masks the true potential of the region. By fireworking off these smaller, incomplete discharges, the huge active region appears to be busy, but not threatening in a singular sense. But if we view it as a transitional phase, then the busyness is just the vibration of the engine before the car actually accelerates. So, we have a system balancing between decay and detonation. We have a boiler that is rattling. We have an oscillation that could last for days or end in an hour. This puts us in a position of attentive anticipation. We are waiting for the coin to drop. But while we watch the physics play out 93 million miles away, we have to deal with the reality that these incomplete discharges are still sending waves of energy toward us. Even a stuttering sun has leverage over our planet's environment. The impact of such processes on Earth goes far beyond beautiful auroras and temporary communication disturbances. This brings us to the practical reality of living next to a star in transition. It is not just about the light show. It is about the invisible connection between that oscillating magnetic field on the sun and the grid that powers your lights, the satellites that guide your car, and the very air above your head. In the next section, we are going to break down strictly the technological collateral damage of this event. What happens when incomplete discharges slam into the global magnetosphere? The answer involves electrical currents in the sky and risks to the systems we rely on every single second of the day. Given what we now understand about the transitional oscillating state of this active solar region, we have to bring the focus down to Earth. The uncertainty of the solar dynamics does not mean the effects here are theoretical. They are physical and they are measurable. The impact of such processes on Earth goes far beyond beautiful auroras and temporary communication disturbances. We are talking about a fundamental shift in the electromagnetic operating environment of our planet. During strong magnetospheric disturbances, which are triggered by even these incomplete discharges we have detailed, electrical currents intensify in the atmosphere. This is not just a light show at the poles. It is a surge of energy that flows through the ionosphere, the layer of charged particles that sits high above us. When the sun pushes, the ionosphere pushes back, and that interaction generates induced currents. These currents do not stay in the sky. They induce parallel currents in the ground and, more critically, in long conductive structures. This directly affects satellites, navigation systems, radio communications, and power grids. Let us start with the satellites. The structure of the ionosphere changes during these events. It swells. It becomes turbulent. For a satellite in low Earth orbit, that swelling atmosphere acts like a sudden patch of thick fog. It creates drag. The satellite slows down and its orbit decays. Operators have to burn precious fuel to boost them back up, or risk losing them entirely. Furthermore, the flow of charged particles increases, bombarding the sensitive electronics on board. This can cause bit flips, phantom commands, or permanent hardware damage. We are seeing a space weather environment that is hostile to the delicate infrastructure we have placed in orbit. Then there is navigation. GPS and other satellite navigation systems rely on sending a signal through the ionosphere to your phone or car. When the structure of the ionosphere changes, when it becomes rippled and dense with solar energy, that signal gets bent. It gets delayed. A delay of a billionth of a second can mean a location error of meters on the ground. In the middle of a strong disturbance, your navigation might tell you that you are on the parallel road, or the drone delivery system might lose its lock. It introduces chaos into systems designed for precision. Radio communications are the next casualty. High-frequency radio bounces off the ionosphere to travel around the curvature of the Earth. When the ionosphere is disrupted by these solar oscillations, that mirror shatters. Signals fade out, static takes over, and transpolar flights have to reroute to maintain contact with traffic control. But the most significant risk is on the ground. Power grids. The same induction principle that affects satellites affects the massive transmission lines that crisscross our continents. These lines act as giant antennas, picking up the geomagnetically induced currents from the storm above. This extra current flows into the transformers, the heartbeat of the grid. Transformers are designed to handle alternating current, not the direct current spike from a solar storm. This DC current can cause the transformer to overheat, vibrate, and even melt. In extreme cases, it can trigger widespread blackouts as safety systems trip to protect the hardware. It is tangible. It is metal getting hot because the magnetic field of the Earth is shaking. It is far more significant for engineers, satellite operators, and specialists in communications and energy systems than for the average observer. These are the people who are not sleeping right now. They are the ones monitoring the G-scales, the measure of geomagnetic storms. They are the ones putting satellites into safe mode and watching the voltage on the transformers. It is in these fields that tangible consequences may arise, requiring increased monitoring and preventive measures. The incomplete nature of the solar discharges we discussed in Chapter 2 actually makes this trickier. If it were one big storm, we could weather it and move on. But this series of events, this partial retention and slow release, creates a prolonged period of stress. It is not a single punch. It is a rapid-fire series of jabs. The ionosphere does not get a chance to recover before the next wave hits. The grid operators have to remain on high alert for days, not hours. The unstable energy mechanism on the Sun is effectively broadcasting instability to our technological infrastructure. We have built a civilization that runs on electricity and precise timing, and both of those distinct pillars are vulnerable to the whims of stellar magnetic dynamics. We often think of space as out there, separate from us. But when the currents intensify in the atmosphere, space is touching the wires in our neighborhood. The distinction disappears. The active region on the Sun becomes a component of our local electrical circuit. This technical impact is the hard, measurable side of space weather. But there is another layer to this story that is often overlooked in the rush to protect our satellites. We are biological organisms living in an electromagnetic environment. If the grid can feel it, can we? In the final chapter of this deep dive, we are going to look at the controversial but growing body of research concerning the influence of these space weather events on human biology. We will examine why some people might be feeling more than just anxiety about the news, but a physical response to the storm itself. This connects to a question that hits closer to home than any satellite or power grid. what about us? In addition to these technical effects we have detailed, a growing number of studies also point to possible influences of space weather on living organisms, including humans. The human body is not isolated from the environment. It is, in essence, a complex electrobiochemical system. Every thought you have, every beat of your heart, every movement of your muscle is driven by tiny electrical signals. Nerve impulses, heart rhythms, brain activity, and hormonal processes depend on subtle electrical and magnetic interactions. It is a finely tuned orchestra of electrochemical flow. So, when we look at the data showing that during strong geomagnetic disturbances, the parameters of the external electromagnetic environment change, we have to ask if that external change impacts the internal system. The science suggests that for some, the answer is yes. This may affect human physiology in ways we are just beginning to catalog statistically. Statistically, periods of increased complaints about headaches, insomnia, irritability, blood pressure fluctuations, fatigue, and reduced concentration have been observed during these solar windows. It is a correlation that appears in medical data and occupational health reports. When the Earth's magnetic field is rattling, reports of these nonspecific symptoms tend to tick upward. In sensitive individuals, symptoms of anxiety, depression, and emotional instability may intensify. It is not necessarily that the storm causes these feelings, but it may act as an amplifier. If the body's own electrical rhythms are being subtly nudged by the shifting geomagnetic background, it creates a physiological noise. This noise can manifest as a feeling of unease, a disruption in sleep cycles, or a sudden lack of focus. However, we must be very careful not to overstate the danger here. For most people, current solar activity is in practice more of a cosmic background than a real risk factor. The human body is incredibly adaptable. We evolved on this planet, under this sun, and our biology can handle the typical ups and downs of the solar cycle. You are not going to be struck down by a magnetic wave, but acknowledging that there is an interaction is part of understanding the full picture of this event. The influence is subtle. It is the kind of thing you might notice only if you are looking for it. A night of restless sleep, a headache that won't go away, a feeling of being off while the solar monitors are flashing red. It is a reminder that we are biological creatures living in a magnetic universe. Ultimately, we are witnessing a rare and complex phase in the life of our star, where stability and chaos, accumulation and release, predictability and uncertainty intertwine. We have covered the physics of the impossible accumulation, the mystery of the overheated boiler, the theory of the transitional state, and the risks to our technology and our biology. This anomaly does not yet pose a direct threat, but it offers a unique window into how stellar magnetic systems operate at the limits of their capabilities. We are seeing the sun push against its own constraints. We are seeing it experiment with energy states that we struggle to model. Perhaps in a few weeks everything will dissolve into ordinary solar dynamics. The trapped energy might dissipate, the active region might decay, and the overheated boiler might cool down without incident. Or perhaps it will enter history as one of the most unusual episodes of the cycle, finally releasing that accumulated tension in a display of power that we will be analyzing for decades. For now, the sun seems to be holding its breath, leaving scientists in a state of attentive anticipation. And that is where we leave it today. We are watching, we are measuring, and we are waiting to see if the breath is held or if it is released in a shout. If you found this deep dive into the solar anomaly valuable, please hit the like button. It helps the algorithm share this scientific analysis with more people who need to know what is happening above their heads. Stay curious, stay observant, and I will see you in the next update.